I think that we can get started. What I was thinking about this session is maybe like, as this is the first very dedicated session about like the minimal zkVM and leanVM, what we can talk about is like the general architecture and maybe discuss about it, as I know that there are many zkVM experts in the room. Probably this will be like a full discussion. So it's just a paper written by Emil on the minimal zkVM. So yeah, I think that we'll be able to go through this paper and maybe we can dive step by step. Don't hesitate to ask questions, suggestions, remarks. And
I don't know to what extent, because there is this leanVM day, to what extent we should come back on the VM in itself, or if we should focus on the proving system.
maybe we can go to the VM, just like
The VM in itself?
Yeah, just the paper, like first the algorithm that we want to have.
So, okay, to begin with, the goal of this VM is to prove a single program that will be able at the same time to aggregate XMSS signature and to handle recursion to be able to verify aggregates of aggregates. So we need at the same time to verify XMSS and to handle recursion in the same program. So this VM is designed for only one program in mind initially. The field collabel for its nice Poseidon properties.
Sorry, Emil.
Yeah.
Scroll up. So I think signature verify should take as input also the slot or epoch.
Yeah, correct. Correct, indeed.
I think that maybe like the diagram that is just on the top could be detailed with like the bit field and stuff. This one, like, yeah, this is interesting maybe just to understand how we aggregate like the bits represent like the different validators, and then you have an aggregate seed that's just concatenate like the three signature. That's how like you generate the stuff.
Sorry, quick question, because you just mentioned the field, and maybe this is the wrong session, but why not use binary fields? Like, was there a reason to go with Cloudberry?
Is the security of Poseidon on the binary field?
No, but then you can use more classical algorithms.
Yeah, it's a fair point. I think it's definitely a possibility.
We did some experiment at the beginning of the year with that. I think that there is also a paper about like using binary field for Poseidon that is currently written by Dimitri and other guys, which is under construction. What we have done with classical hash is that at the beginning of the year we tried like a different proof system like Venus and also Hashcaster by Leb with Ketchak and more traditional hash function. The final goal of this experiment was that it was much slower, like to prove what we want compared to this on CPU, as this is what we target. So that's why we switched like to Colab.
But it's definitely interesting.
Yeah, for sure.
No, it's good to hear that you guys ran experiments before.
Yeah, but maybe the number have changed since then, and we can even maybe revisit the proof system and stuff. We just because like the signature scheme that we have to verify involve many hash. So what we have to prove are hashes, and we just try simply as a very first benchmark to prove as many hash as possible with various proof systems. So for example, how many times can it take to prove Ketchak using Venus or using Hashcaster? How many times did it take to prove like Poseidon using Blocky3? And the result of this experiment was that by far proving Poseidon through fry techniques or weird technique was much faster than the other.
When was that?
Sorry?
When did you do the experiments roughly?
It was January of this year.
So quite recent.
Yeah, but all of that evolves really fast, so not that recent.
Regarding the API, you are currently as input you have the signatures, you have the bit field, and you have the slot. But if you force that on the crypto library, it becomes very Ethereum specific. So can't we just have the signature and the build field and the slots would be handled at the client level like it is right now in the Bitcoin chain?
So the thing is that the signature scheme needs a slot, whereas in BLS you don't need the slot, right? The slot is really, that's why I said verify. Signature.verify should take as input the slot, right? And I think it's also not that bad if like at least the crypto libraries that we develop are specific to Ethereum. I don't think that's that.
But the goal of Justin was that it's useful for.
Sure, but okay, maybe then I take that back. But I guess you still need the slot because it's part of the signatures. Okay.
I mean, sometimes the slot is a part of a secret key.
Sometimes the slot, in general, if you look at just XMSS outside of Ethereum world, then the slot will become a part of the secret key. Whether it is reasonable to model it this way here, yeah, I would also probably think of like, since the slot is coming outside of from the environment essentially, then it makes sense to move it as a extra field.
Yeah, please continue. I think also this is interesting, like the first line of this mentioning why we chose like a koala bear instead of baby bear due to this interesting automorphism that makes it very, very efficient for Poseidon compared to baby bear.
Talking about binary fields, I had a discussion on Gem this morning, and I learned about this new field, ghash, in the context of stocks. It's a 128-bit field, and my understanding, correct me if I'm wrong, is that it's a great field for CPUs, but less good for GPUs, because in CPUs you have like custom acceleration, but not on GPUs. And in our use case, we are primarily targeting CPUs, but there are synergies with all of the other work that we're doing on zkVMs, for example, where we do care about
ghash is used in AES GCM?
Yes.
Yeah, so as much as I would love to have a good alternative to Poseidon, we haven't been able to get anything that's in the realm of like 1 to 2 million hashes per second or whatever. I'm optimistic that like maybe there's some way, but I don't have an alternative right now. On ghash, yeah, this is like the kind of standard 128-bit binary field extension that is used in AES GCM mode. It is the fastest finite field on CPUs because of, or on x86 and ARM because of the carryless multiplication instruction that's like optimized for that. We have started to take a look at the new Poseidon 2B work that Dimitri and collaborators have worked on, and also implemented like vision over ghash. As soon as I, get something that's not in the realm of what this can do, yeah, I would say so. My personal opinion is still that Crosstal is the most is the best zk hash function for a variety of reasons. But I mean, on Poseidon, there's the security stuff. I mean, one of my concerns is just the native computation speed of it in comparison to other hash functions, which is sort of undeniably slower than things that are like bitwise optimized. But I get the considerations around this.
Right. My hope, thinking long term, is that eventually we'll have CPUs with Poseidon acceleration, at which point we'll be in a very, very good position.
They still don't have catch-up acceleration.
Right, good point.
Easy, go on.
Can you show the automorphism? That is an efficient automorphism. Can you show it?
The idea is that for Poseidon, you want for the S boxes you need an exponent, which is another automorphism, and for baby bear, the smallest one is 7, and for koala bear it's 3.
Okay.
And simply in your arithmetization, we'll have cubes instead of power to the 7, so it's simply faster.
Okay, no, I thought it was spatial automorphism. Okay.
No. It's simply like the cube isn't of it.
So the degree is great, okay.
Just factor p minus 1.
Yeah, sure.
Yeah, that's it. And so, if we want 128 bits of security without the conjecture, like even with the conjecture up to capacity in WIP, we probably need an extension degree of at least 5. And I believe that with the current, like if we target 128 bits of security with the current of proven security, we probably need extension 6. But currently, implementation is degree 5 with conjecture up to capacity. The memory of the virtual machine is read-only, as in Cairo, and it's a big vector of read-only memory that is committed as a multilinear polynomial. I didn't mention it, but everything here is multilinear and some check-based.
Maybe this is interesting to know two things. First, why we chose like read memory instead of read-write memory. And second, I think that another difference with Cairo is that they have this notion of segment, while in the current VM we have only like a single segment with a big vector with all of the elements.
So first, why read-only? I would argue for simplicity, and the main advantage of read-write is that writing a program is easier, more natural when it's read-write. But in our case, because we only need to write only one program, I would say that I would prefer to make it a little bit difficult if the proving system is easier and more efficient at the other side. And about these memory segments in Cairo, I think it's for the precompiled, but like some parts of memory are dedicated to some precompiles. And in the current implementation, it's not the case. Like the memory is a single segment, and the precompiles are handled in a different way with lookups from air tables into the memory. I will come back to this later.
I'm not so much into that, but isn't one of the main arguments for the non-deterministic read-only memory versus read-write is read-write helps if you do continuations, because you need to fingerprint the memory state at the current point in time and want to reuse it later. But in this application, you wouldn't target something like it, right?
Exactly. No continuation.
Yeah, so it seems like natural choice. No?
Quick comment on the read-write. So my understanding, it's more of a question of the extent of sort of user experience for the underlying VM. So you can express a lot of really powerful programs using the read-only paradigm, which I think is why a lot of people in industry have opted for that, because it's substantially easier to have basically an almost immutable memory trace, and that sort of makes sure that you win a lot. Now, in a sense, I would say that the real question here is the developer experience. So a lot of people, the way that they code and the way they write smart contracts, utilize read-write just because that's how we do it in the processor. Whereas I would say that the issue is, are we okay with using and developing a specific VM ISA that is restricted only to read-only and is efficient if these sort of developers are okay with sort of structuring the way that they write programs to utilize that as a base. And so that's more of a question of what is your ISA and zkVM going to be used for. So I think, and correct me if I'm wrong, Justin, but in the case of the leanVM, you guys are fundamentally interested in doing very specific checks with super hardened and audited contracts. And there is, I would say, very little chance that you cannot do what you want without read-only. So that's the first comment. And the other thing I want to say is, if we're going to go into the paradigm of read-write, And talking fundamentally from like an information theoretical tonality perspective, you have to make sure that the memory trace has to contain every single additional change, and there has to be sort of a data structure that is temporal. So as you know, you have your base memory, but then every single time you write or change the memory, you're going to have to augment this, and there's no way around it, right? Because you need to make sure you do that. So I would say the open question is fundamentally based on your motivation. But it is possible to do, but you need to make sure that the way you arithmetize your memory allows you very efficiently to be able to check all these updates. And I think that's an interesting problem. But in the case of leanVM, it may just be the case that that thing won't be interfacing with your end user devs. It would be more kind of like people like here who know exactly what they need to do because it deals with sort of the guts of the protocol. And I would say in that kind of applicability, in that kind of context, read-only is both more efficient, simpler to audit, and sort of like fundamentally pushes a lot of the burden on us to make sure that it's ideal and perfect, and sort of takes that trade-off. So I think it's definitely feasible, but it's more of a UX issue in my view. I don't know.
I fully agree. I mean, also Cairo and Stockwell uses read-only for that reason. But what I've heard, but I'm not sure because I'm not much into it, though I'm at Stockwell, is they're reconsidering it for the reason of continuations.
I mean, I can speak. I mean, I know the Caribbean quite a lot, and Stockwell team as well. So I don't think that they are about to change the Caribbean anytime soon. But it's actually true that the Caribbean, as it is done today with the read-only memory, prevents from doing continuation. And the problem is not that much due to the read-only memory, because you can snapshot the read-only memory, you can make a commitment of the read-only memory anyway. The problem is that there is a relocation step at the end of the process of the Caribbean, meaning that the addresses are known only when the program exits. So you cannot start proving if you have not exited the program. So this is the main blocker for the continuation currently. But you can do then, because it's like in the Caribbean, but the memory is not 1D, it's 2D. So you have segment index and segment position inside the segment, which gives you a nice property of being able to do dynamic allocation at runtime without like in a real malloc, for example, you need to give the size of the segment that you want to allocate on the heap, for example. But in the leanVM, you can just alloc and it pops a new segment. You can write infinite, up to the feed size, of course, number of value in the segment. And then at the very end, they are all concatenated to form the one-dimensional memory that is eventually considered read-only from the prover point of view. So the limitation for the continuation is this relocation step. You could do a prover that would keep the memory two-dimensional, but then the memory would sort of have a lot of holes, so you lost a lot of space. Yeah, I don't know what the question was again. Precisely, but yeah, about the Cairo things, this is how it works.
From a UX point of view, if we really want to push all the thinking to us, we really have two use cases. One is aggregating aggregating signatures and generate a proof, and the other is aggregating proofs and generate a proof of proof. So the alternative is writing two circuits, one for each.
So I think the significance of the read-only memory is not that it's a UX consideration, but it actually means that the leanVM bytecode is not a programming language, or if you consider it to be a programming language, it's not a Turing-complete one, because so there's no div opcode, for example, in this language. There's add and mul. So what you can do is check a division using a multiplication. And so, like, in order to implement division, you would need some extra thing outside of the bytecode that, that says to put the result of the division in the appropriate place. And that's how stuff works all over the place within this leanVM design. So I think rather than looking at this as a VM that implements a programming language that you could just execute to perform a computation, it's more informative to look at it as a system for expressing constraints.
Yeah. Constraints with control flow.
I agree with that analysis to a large degree. Yeah, so I agree with that analysis to a large degree. However, I would say that you do have the designer freedom to pick the opcodes that are fundamental. And I think that it is possible for you to have, I mean, there are languages that exist, Lisp-like languages, with some caveats on the underlying data structure, which actually can exist with one or two, basically two real opcodes and then some memory, lookup opcodes, which are completely Turing complete, and you are able to sort of work with that. So my comment on this would be that it's not something that is directly impossible. It's just a question of judiciously choosing the opcodes that you are actually going to enshrine in your base, and you won't sort of run into that wall in general. So you will be able to resolve this concern. Now the issue is with that, whether for me to be able to compute a program that I care about, I'm going to need 10 billion opcodes or not, and that's sort of a fundamental trade-off, which I guess. If we sit down and churn into a super optimized use case for the two specific cases that we want, we might be able to resolve it. But I would be a little bit less optimistic that a dev who wants to write in this would be able, without sort of some kind of compiler or optimizer that is sort of given to them out of the box, to actually go and do that kind of work to make a really efficient program. So it's more of a question of making sure you pick things that give you the freedom you want. And then again, are you okay with most people not using this and instead coding on EVM and using EVM and zkVM sort of products to do that execution, and keeping this as something more of a base layer plumbing level VM that we know for a fact is 100 billion% secure, that we are comfortable zking the consensus layer or zking some kind of fundamental signature aggregations as part of the L1. So in that context, I would say that it's much more responsible from the perspective of security to have a system that is fundamentally auditable and secure, even though we pay for it in sort of the expressivity of our language downstream. But there is a world in which that language is as small and as sort of compact as leanVM, and is still Turing complete.
100%.
That is possible.
Yeah, BrainFuck has 5 opcodes, and it's Turing complete. 7.
Yeah. So
there's also one that just has 2. There's the SK combinator calculus.
Yeah, so actually, it's funny you mentioned SK combinator calculus, because the way I stumbled into this was I had to design a VM for a very specific small Lisp-like language called Knock. And Knock, I think, is that calculus that you mentioned. It's one of those. And what it's a little bit clever in, so actually the first 3 opcodes of that language, so the first one is just the memory lookups, and then the second and the third are actually a little bit funky, but those 3 themselves actually give you full Turing completeness. So they call it baby knock. So there are solutions for sure.
Yeah, and I might have overstepped in saying that it's not Turing complete, because I don't actually know that for a fact. But either way, the fact is that practically speaking, you wouldn't be able to implement the programs you want to implement in terms of computations, within this language without some external thing that is filling the memory with the right answers. Because that's not what this is for. It's not for running computations. It's for checking the answers.
Yeah. You can also get opcodes that are macros of the fundamental opcodes, in order to sort of alleviate the concern that a lot of people would have about sort of, in a sense, coding in bytecode. right? You can do that, and that would actually be relatively easy to implement if you have the fundamental opcode secured. It's sort of like a precompile, kind of, but you can sort of like harden that into your ISA and just have very, very generic sort of links between your more complicated opcodes. Like you can, for example, like hardcode an if statement opcode on top of the first 2 or 3, and then that just becomes a question for us here, like what is the most clever way to do this so that I can give people the fundamental things that they require in order for this to even be usable in UX. Because there is a world, in my view, where you harden this and you do all the really important stuff with it. You sort of demonstrate security downstream over time, and then you build on top of that something that resolves the UX questions. Of course, that's reaching, but I definitely feel like that is possible.
But in that case, instead of having a macro that creates the bytecode, we can also have a macro that creates the circuits directly.
By bytecode, I mean circuits. I'm operating on top of the AIR when I say macros. I mean that like the constraints that are used by opcode 1 and opcode 2. Then if you have opcode 3 that does something on the first 2, you can sort of like figure out hard-coded constraints that leverage the other 2 in order for you to get that. I'm not operating on the CPU. I'm talking about.
Okay, because right now the leanVM has a DSL that's compiled down to a bytecode that then is compiled to a circuit. So when we talk about bytecode, we need to make sure we talk about the bytecode there rather than the circuit below, and vice versa.
Yeah, although I mean, at the end of the day, there's also a question of whether, so I'm running the program computing, right, and I'm getting the bytecode, the real bytecode. But at the end of the day, if you really want to get really high efficiency on these things, the real question is the transcription from the bytecode that you get in real life to the equivalent sort of circuit representation of this in field elements. That's really where the massive efficiency gains come in. Because all of the bytecode sort of like compile, like efficiency work that's gone over the last 20, 30 years in building really efficient compilers, that work is basically what we need to do at the circuit level to make sure that that's as optimal as possible. And I think the design space there is a little bit different, but I agree with you, but I would focus on sort of how do we get that representation of the bytecode at the circuit level as optimal as possible, and what kind of restrictions can we put on the way that that bytecode is generated, so what structure can we impose on it so that we don't have to do really expensive things at the circuit level, if that makes sense.
Sorry to have opened such a huge debate. Please, last question and then we move on. So
just a couple of comments on our experience with the Petra VM, which was a VM that uses a read-only memory model. I believe in this model. Like, what we basically did was we had a read-only memory. We tried to design a high-level functional language, which is a strict subset of SML. Ben actually wrote like a shit ton of SML, and I liked the approach we ended up taking, which is you can write code in that, and as long as it complies with the subset, you can run like a normal interpreter, so the DevX was good. Our experience overall was like the amount of effort it takes to write a compiler, even for a very basic functional language, which is like, I assume something that would be easy because it's from like college textbooks. In practice is quite difficult. I do think it's expressive enough. My general recommendation for this application is just straight circuits to sidestep the entire thing. Maybe that's going to derail this discussion, but that's
that is a very interesting point, and probably this is the right moment, as I see on the screen, like the different opcodes. Probably this is the right moment to have this discussion. I know that Clément and Robin may be a bit familiar with this new approach, avoiding the compiler stuff, playing with the hairs instead. We just discussed that briefly with Clément at the beginning of the day, because I think that with Cairo they have similar experience, and this is the approach they have taken for the new zkVM design, instead of having a compiler playing with circuit and stuff. So maybe Clément, if you want to take a word about this.
I'm not so sure about the question, but I'm fully aligned with OpenVM for anyone who has read the OpenVM paper. And so the basic idea, I think, is just to not make hard decisions about the opcodes that you want to use, but just make sure that you build a framework that you can add on top of the kind of chips, as they say, components, as they say, stuff, anyway, that you want to add, which are at the end just sort of independent circuits that are all bind together with lookup arguments, so that you make sure that you keep a global consistency. But you don't need to think about a global ISA, but more about independent circuits that communicate with lookup and that overall needs to be all consistent with each other in terms of the value they put or pull from the lookup argument.
I think this is what you just mentioned, right, Jim?
I mean, I would not use errors. I mean, we're basically using Spartan non-uniform circuits. You basically don't need to pay for lookups. Wiring is quite cheap, and you just. I think it's going to be easier to do formal verification for that sort of thing too.
Using single circuit.
Yeah, a single circuit for like the leaves, and then you have 2-to-1 aggregation, and you can sort of, in order to get variable sized, larger statements, you're just playing with the recursion architecture.
I believe it would work. The question is, what is the simpler approach? And for me, it's not 100% clear yet. Yeah. Because indeed, in your approach, you have one big circuit, and that's it. So it's hard to prove that circuit is good, but when it's done, and you are quite confident in it.
Emil, I think it could help if you can explain the state of the compiler. Like, is it finished? How many lines of code is it?
It's not finished because it's not perfectly stable. It's like currently approximately 5,000 lines of code. When I would say we don't really care about the compiler, what we care about is the produced bytecode. Once the produced bytecode has been created, we can remove the compiler because we would formally verify only the bytecode, the result. Well, so the compiler, yes, I know that's some other approach, but one approach would be to have like a formal specification of what you want to prove and to formally verify that the program with this minimal ISA does what you want it to do. And in which case the compiler is just used to help you write the bytecode, but when it's done, you don't care about the complexity or the correctness of the compiler because you will only prove correctness at the bytecode level.
And there is an alternative. It would be formally verifying the constraint. And in that case, we can also discard the bytecode.
Formally verify which constraints?
So you have currently you have compiler, bytecode, and then another step to convert that into constraint, right?
The bytecode is like this bytecode with those 4 opcodes, and you have a trace. Each cycle you execute one of these 4 opcodes, and that will interact with memory. And the circuit is used to prove validity of this execution. There is no really a compilation from this ISA to a circuit that will depend on this ISA. The circuit is only used to prove the validity of this execution of this ISA.
Do we foresee the recursion circuit changing a lot or not changing too much? Because I understand that we are doing world verification, but how much of the world stuff is going to change in the next few months? Is there World 2.0? What is going to happen here?
One advantage of having the ISA approach is that it's easier to adapt because your program is like a few thousand opcodes, and so it's probably easier to change some part of the program than to change if it's a big circuit.
It's not obvious to me that it's easier to verify the compiled code than to verify the source code and that the compiler is preserving the semantics. Because like proving that a simple compiler
also, how confident are we in being able to formally verify anything we produce? How confident are we that the formal verification stack is going to be ready in time? Because if it is not ready, then we will have to rely on extensive testing, rely on a lot of checks.
I think the idea is really to rely on formal verification, 100%, but you will have to ask Alex how hard or easy will it be.
I think that right now, like, they are building like the building blocks, such as some weird primitives, some check primitives, and some basic primitives, so that we can reuse all of their components. For the full stack is not ready, but yeah, we rely on that for the future.
Okay, but what's our backup plan if that's not going to be ready soon? Because better to have stuff in between than to wait for the thing to be ready.
Having the thing like very well tested with fusing, with all of these kind of best practices.
It won't be ready, if you mean by soon, in less than 2 years, it won't be ready. But
this will not be deployed in production.
Yeah, the goal is to deploy this in 4 years.
Okay, no more questions. So in addition to our evidence, I will quickly come back. There are those 4 opcodes that interact with the memory. And basically you are able to have arithmetic constraints, add and null on your memory, and you have conditional jump to have control flow, if, else, and some kind of functions and loops. And you also have this dereference opcode that enables you to communicate information between different parts of your memory. And in addition to those 4 pretty simple opcodes, currently there are 4 precompiles. The 2 of them are used everywhere because both in XMSS aggregation and recursion we need a lot of hashes. The 2 last ones, dot product and multilinear evaluation, are used in recursion. Dot product enables you to perform, as its name suggests, dot product, but in the extension field, which is really important because the initial opcodes act at the basis field level. In regression, you want to be at the extension field level, and if you have this dot product, you can basically perform multiplication doing the product of size 1, and you, most importantly, you can fold large chunks of your memory, which is necessary in WIR. And multilinear eval is also used in recursion, but it's like a detail. One thing to note is that contrary to K-row, there isn't such thing as an allocation pointer register. So when you want to call a function, which is like, the notion of function is not enshrined in the ISA, it's an abstraction that you can create on top of the 4 opcodes. A function basically lets you jump to another place in memory. Yes,
yeah, just a question, because you say there is no call or code. So when or how are you updating the frame pointer actually?
When you jump, you are able to modify the frame pointer. It's like one restriction that lets you potentially update the frame pointer. Like it's one jump that does everything you want to do. And the key idea is that when you want to jump to a new function, like you want to call a function, you will receive as a hint the location of where to jump. And the idea is that because it's read-only memory, no prover can cheat, because if it was read-write, the prover would make you jump at a previously written location in memory. And because it's read-only, you cannot destroy previous memory, and that's why you can remove the allocation pointer register. And one thing is that when you jump to a function, before jumping, you need to write, using the DRF opcode, your current program counter and frame pointer to be able to come back to your previous context. It's like a detail, but just to the high-level idea is that you can have you can design functions using those sort of codes.
I think that the main goal of AP is to be able to have a dynamically sized frame at runtime when you don't know the size. I mean, if you want to do a number of loops that you don't know, it's just provided as an input, for example, then you need AP for sure. But maybe in your context, you just have fixed size frames and you know how many times you're going to do them. That's why you can remove the AP.
You can remove the AP because you can transform the loops into recursive function. You let the compiler, indeed, if you loop, you know the number of iterations at compiling time, you can unroll it. But if you don't know, you can simply transform every loop into recursive function. Are you convinced or not?
Yeah, but there is normally, if you do this, no, because you have no call-up code, but in the call-up code, normally you need to store the place where you need to go back.
Yes.
Well, you don't store where you go back, so you can unfold an infinite number of frames, but then at the end of the day, how do you prove that you eventually sort of finalize a program that has been done, like, so that you come back to initial place?
Actually, before jumping, you will write down at the beginning of the new frame your current PC and your current FP.
So it's like a code, but at the very end, if you write this down and you don't have any AP,
and so you write it down, you jump, and then you execute your function. And at the end of the function, there will be an opcode, jump again, to come back to your previous context, that will update the PC with the value of PC that has been written down at the beginning of this new frame.
Well, this is the call-up code at the end, how it's done in Cairo. It's just write the two values and call. It's just, a call-up code in Cairo is basically writing FP, return PC, and jumping.
Okay, yeah.
How do we make sure that the program terminated?
It's a good point. When you define a program, you must give the list of instructions, and you must give a special line which is like the final line. And in the proving system, you will assert that at the end of the execution trace, you have indeed ended up on this line. And this line actually it's a jump that will make you jump in place. So you can execute it. So the idea is that you can pad the execution table with this line. You can pad it until the next power of 2. And you simply assert at the end of the execution table that you are indeed on this final line.
Got it.
Actually, you assert that on the execution table, you need to assert two values, that the first PC is 0 and that the last PC is the final PC. That is part of your bytecode. Okay. And one funny thing is that using this dereference opcode, you can do range checks. Because basically deref lets you access some memory value based on an address. And this will fail if the index, the address, is bigger than the memory size. And using it, you get a check that some value is smaller than the memory size. And if you check that, for instance, if you want to check that some value x is smaller than 10, what you do is that you check that x is smaller than the memory, and that 9 minus x is also smaller than the memory, meaning there is no underflow in the subtraction. And using this, it's a weird way to have efficient range checks using the dereference opcode.
And in practice, what happens when you exceed the range? When the program...
No valid proof can be generated.
Okay, but the program continues?
You could make the program run, but the validity proof will not be... will fail to generate or will fail to verify such a validity proof.
This is where it may be helpful to think of this as a way of expressing constraints rather than a way of computing.
You can do efficient switch assessment, but it's not really important. Maybe don't know how much time we got left, but quickly, the proving stuff, we can quickly talk about the architecture of the proving system. Everything is...
Maybe this is not just to go to log up in detail since there is the afternoon session about this. This is not useful if you want to gain time to go through the log-up start since there is a full session this afternoon.
Okay, indeed, okay. So without talking about log-up, everything is multilinear, meaning you commit, like your memory is a multilinear polynomial, your R tables are multilinear polynomials. Actually, you can interpret every R column as a multilinear polynomial. But you will not commit to all those multilinear polynomials individually, as you will do if it was in K-row or more generally in the univariate case. What you do is that you pack all those multilinears into one big multilinear. There are multiple ways to do it. One solution is the jack PCS. You concatenate everything, and the key point here is that if your columns have some padding, using the jack PCS, you can avoid committing to the zeros. So you can gain up to a factor of 2. Because you do not commit to the 0, you pack all the non-trivial parts of your columns together. You obtain a big multilinear polynomial that you commit. And using an appropriate sum check in the jack PCS, you can reduce claims of every individual columns to claims on this big multilinear polynomial. And then you can use your PCS, WIR, and so on. But actually, there is a way, I believe, to reach almost the same performance, actually, potentially even better performance for the prover side, and in a more simple way, without using the sum check of the jack PCS. Basically, the idea is that you will cover every non-trivial part of the columns with power of 2 chunks. You may commit, for instance, here you commit to a bit of zeros because your power of 2s, for instance, if you take 3 or 4 power of 2 chunks per column, you will go a little bit beyond the non-zero part of the column, so you commit a bit to 0, there is some padding, but much less padding than if you commit to it entirely until the next power of 2. And then you put all these chunks into a big single multilinear polynomial. Importantly, you start with the big chunks. It is important to have some alignment, to have a good alignment. And you can reduce evaluations on each column, 2 evaluations on each chunk. And you can reduce evaluations on each chunk, 2 evaluations on the big multilinear polynomial. And one advantage of this approach versus the jagged one is that you don't have a sum check. One disadvantage is that there is control flow in the verifier. So if the verifier is a circuit, you probably prefer the jagged PCS approach. In our case, currently we have some control flow, so that's why I believe this approach is potentially simpler than the jagged PCS.
Maybe something interesting there is to mention as multilinear things that are like a new things when compared to the univariate. What are the pros and cons? What are the difficulties and the main advantage that we have by using multilinear polynomial instead of using the classical way with Fry of univariate?
The main advantage I see is that you will reduce the proof size because you can, as explained here, you can pack almost everything into a single multilinear. Because if it's univariate, you need to commit to every column individually. Okay, you can have a batched Merkle tree, but you will have some kind of Merkle opening for each column. And so if you have 1,000 columns, your proof size will be likely above 1 megabyte. In this case, the Merkle opening will be on only one big multilinear.
And then with this new approach, we also have to deal pretty much everywhere with the subcheck.
Indeed.
And then we need to find out source of possible optimization to optimize these new tools that comes into the room.
Indeed. So you can prove validity of Airtables using subcheck. It's pretty efficient. For instance, currently we can prove like on this Mac, you can prove almost 600,000 Poseidon per second, whereas on Plonky 3 in the invariant approach it's a little bit more than double with the same parameter. Actually, using degree 5 extension of Colabert, while in Poseidon it's a degree 4. In Plonky 3 it's a degree 4. So probably if we take the same parameter, the same conjecture, we can likely go to like 800,000 maybe. And also, to answer the question, one advantage of the multilinear approach is that you can use global star, which is, I believe, which saves a lot when it comes to the fetching the opcode that represents the instruction.
I'm not sure if this is the right way to go. I also saw that the Google team was taking that idea, which is probably well known under the Fourier people, which is that you use a mixed radix FFT, so not just powers of 2, powers of 3, for one reason, because we can approximate a given domain column length better.
Yeah, so you get less padding overhead.
Sorry?
You remove some padding overhead, like instead of having...
Yeah, exactly. You tailor your domains to the given execution trace line.
You can do such tricks with the invariant skip.
But I think that we discussed that with Angus and you didn't see that much performance.
Yeah, I can comment on this.
And just for one reason, because for me before the Jack PCS came up, I was not sure if multivariate over prime fields makes much improvement. Because for one reason, the univariate prover has the synergy between the committed values, the FFT, effort done while commit, and constraint evaluation. So you reuse these values, so which you can't in a multilinear. Even if you commit to read Solomon, that FFT work cannot be reused in the subject.
Yes.
And that's why I was never sure since the Jack PCS, and likewise I guess like you say, I'm not so sure anymore. Which is better, you know?
Yeah. Just Angus and
sorry, on the radix thing, I guess there's two things. So one slightly unfortunate feature, I mean, sort of the nice thing about Colabert is that 3 doesn't divide p minus 1. This also means you can't like 3 would be a useful radix for this sort of thing. So you can only do these radix things for like things that divide p minus 1, which Colabert is 2 and 127, so it doesn't quite work as well. The other place that radix comes in is you have like mixed radix FFTs, so you can do like radix 2, radix 4, radix 8, and those work quite nicely when you have nice twiddles. So for like complex FFTs, or I think for Goldilocks, there's some nice twiddles at 8 or 4. We looked into this and couldn't get a huge improvement, but this is certainly something that would be worth looking into.
What again are the prime factors of p minus 1?
It's 127 times 2 to the 24. So the prime factors correspond to like what are the FFT sizes you can take, basically. Yeah. So I mean, the Colabert sort of, I guess the reason we chose it is sort of working against it here, because we chose it explicitly because we didn't want 3 as a factor of p minus 1. So there would be a potential advantage of Baby Bear if you wanted to.
What's the next factor?
127. Also.
Two things. One to Laura's point about the univariate sort of synergy of encoding and constraint evaluation is sort of definitely true, but also when you're in the multilinear setting, you don't need to do the IFFT, you just do the forward FFT to encode, so it does save some work that you would have needed to do otherwise. And then on this, if you use Spartan, you only have one polynomial because all the sort of breaking it apart is done by the wiring check. that's also nice.
It's a good point.
I think that's it basically, because there is also this log up star. Okay, and I believe that the drawback of this approach is that you need to communicate the inner evaluations of every chunk. So if you have a lot of columns and a lot of chunks, you have a proof size overhead. But with a slightly more complex approach of using rectangles with each side of the rectangles must be a power of 2, you can recover your R table and reduce significantly the proof size overhead. Like this. But anyway, this is not implemented, this is just an idea. And there is log-up star, which plays a significant role in the proving system, because it's currently the only lookup that we have, but maybe it's more a topic for this afternoon.
Yeah. If you want, maybe you can show like the nice plots that you have on the README with a number, because I think that we have never showed the number season. So yeah, don't know what you think about it.
Sorry?
The nice plots that you have with a number just in the README. Yeah, where we are, yeah, this kind of plots. Yeah.
So this is on my old laptop. Currently,
yeah, I think this one is relevant.
Currently, I would say the three hard parts of the hard work that remains to be done is to first improve performance by a factor of approximately 4 to 5. Second, to finish the recursion program, because currently we only have a recursion program for a week, don't have the end-to-end thing. And third, all the current XMSS verification algorithm is not the real one with all the tweakable hash and the real encoding, the real XMSS encoding. So there is some work that needs to be done to make it as ZK friendly as possible and to implement it for real in the XMSS program.
On my side, I think this one is quite important, because the plot that you have on the screen, because this represents like how many time it takes to aggregate like 500 XMSS, and so if we reach first the target, that is the dotted line, it will be like quite a significant milestone for the overall project. Yeah.
There are some non-optimizations. For instance, currently the Poseidon recompile we store the two, most of the time Poseidon 16 is used in compression mode, but for Fiat Shamir, actually in the recursion, you need the 16 outputs. So currently we store the 16 outputs every time, and it's it's like a big pollution of the memory in practice when you use XMSS. And the idea was suggested 2 days ago, and we can currently, I think we can reduce almost a third of the memory size by eliminating 8 feed elements of each, of almost all Poseidon 16 outputs. And then there are also some non-optimizations, and then it will be a lot of engineering job to make it fast.
Could you talk a little bit about non-determinism in your design, and also sort of what you are comfortable with and not comfortable with when it comes to non-determinism, and like if you have any concerns about it?
Currently, there are a lot of non-determinism when it comes to function, because when you want to call a function, you need the prover to hint you where. So imagine you are here, you want the prover to give you as a hint fp2, which is the start of the new location, will end up by calling the function. And this value you need to receive it as a hint. And the argument is that from the writer's perspective, you don't care where you end up, because the computations you will perform will be the same, and you will return with the same result. But turns out the prover has the liberty to put this chunk of memory wherever he wants.
Yeah, Will, I think that we are on time, right?
Yep.
So, anything to add? Anyone? Question, remarks, suggestions? Amy, anything else to add?
How many columns?
In the execution table?
No, in the end with pq2-04. It's a single large one, right?
There is like there are 4 airtables and 1 memory. So you commit the memory and then 4 airtables. And in the execution table you commit to 5 columns. In the dot product you commit to like 8 to 9 columns. And in the Poseidon 16 you commit to previously, like in the Plonky 3 arithmetization, you commit to like 155 or 160 columns using degree 3 constraints, like the R has degree 3. But it turns out, if you look at the performance for Poseidon, recently we gained a bit using degree 9 constraints, because in our case, using WIR and using in particular the Poseidon hash function, it's the commitment costs are quite big compared to proving the validity of the R. And that's why reducing, so like you gain something like you remove, I think, 32 columns, but you increase the degree, but in the end it's faster. And so granted that there are something like a little bit more than 1,000 columns here, and I don't know how many columns, but originally it was like 240, something like this, and so now it should be like 200 columns here, maybe.
And what blow-up do you consider?
The rate of the code?
Yeah.
1/2 currently.
Okay.
But one thing that you could imagine is that because it's a collaborative approach to merge those 10,000 or more XMSS signatures, so you could, if you want in the end to have a small proof, you could use 1/2 of the rate 1/2 everywhere, and in the very end you use a rate like 1/4 or something like this to get the minimal tiny proof in the end.
Yeah, but maybe also for recursion.
And also,
that's why
it's potentially we prefer a slightly slower prover, even at the beginning, to get faster recursion. Definitely.